How's it going, guys? So today we'll be learning about nucleophilic aromatic substitution as well as C-C coupling reactions. So to start off, when we're doing nucleophilic aromatic substitution, we'll call this NAS. It involves basically a molecule acting as a nucleophile that will attack a bond. So there's two types. We have addition and elimination mechanisms, and I'll show you an example here. So we have uh, 4-fluoronitrobenzene, and now if we were to attack this with Na plus and OCH3 minus, this fluorine in the para position would be removed and through addition. So this would, nope, my bad. This would essentially attack here, causing this double bond to pop out here. From there, we would then get this, where fluoro and nitro and OCH3 share the same carbon bond. From there, we can put this lone pair onto this bond. We should then kick out this double bond into here. By having that, you can then have a benzene that looks like this, NO2 here, OCH3 with double bonds on each side. Again, we can put these electrons onto here and put this double bond and pop it out through this carbon as electrons. By doing this, we're essentially hoping to eventually kick off the fluorine, allowing the OCH3 to be the same, or to be by itself. So now, because of this, we can put this pair of electrons onto this bond and kick out this fluorine. And essentially, we'll be eliminating the fluorine. So as for here, this would be considered an addition. So by eliminating fluorine, we can get a final product of boom, 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 NO2, and then O. So essentially, OCH3 took the place of fluorine. Now, oppositely, we can also, in this step, have another path. And this path starts right here, where instead of doing that, instead of doing this mechanism, you can go here and have this lone pair drop onto this nitrogen bond and kick out one of these, the double bonds on oxygen, onto the oxygen. From there, you can make another resin structure allowing nitrogen having a double bond and each oxygen being a minus single bond, while still having fluorine and OCH3 on this side. And this is called the Mesmer complex. Mesenheimer, I'm probably not saying that right. Cool. So again, I guess we'll do one last example quickly. For aerial halides, if we were to have Cl and have Na, NH2, NH3 here, this mechanism, we essentially have hydrogen out here where this sodium would be plus, NH2 be minus, would come out and attack this hydrogen, kicking off itself and putting electrons on that carbon. From there, we'd be able to get this where we have 2 electrons minus here. From there, we'd be able to put these electrons onto this double bond, making it a triple bond. From there, we have a benzyne, sorry. So with this benzyne, we can then have our NH2 minus attack one of the carbons of the triple bond, bringing this triple bond back into its last place with electrons on the carbon. And then from there, we have 2 electrons here, NH2, where then we can use the NH3 to grab one of the hydrogens, knock it off, and restore the benzene, which becomes an aniline. Which will be our final product. So I guess enough of that. We can go into CC coupling now. So there's many types of different couplings. Some include Still, Suzuki, Heck, and we'll go through all of that right here. So to start, we have, Still coupling. And that includes called Still coupling. And we'll use this example, Si, surrounded by carbons. With Sn, and we'll use Sn Br3. And we'll combine this with bromine. So this obviously is a halide. So when we use reagents such as PD and toluene at around 80 degrees, you can essentially be able to knock this bromine off, or attach this bromine to this part of the reaction and create a bond, a carbon bond. So the product would look something like this. So we still have the double bond here, but instead of having SN Br3, we can now have this pentagon with the double bond right here. Now, for Suzuki coupling, we'll take an example. Excuse me. We'll take an example such as, we'll go R, doesn't matter what that is, double bond, and put 9 BBN at the top, NaOH, H2O2, H2O. So the big thing with Suzuki coupling is that you use how do I say this? A boronic acid with an aryl or vanillic iodide or bromide. Essentially, that's the couple part. And through that, actually, I'm going to use a different example. My bad. I think this will be a little bit easier to understand. So use essentially boronic acid derivatives. So take this OCH3 again with MgBr, let's say, and we'll have boronic acid, so OCH3, 3. And through this, you can essentially be able to kick off. This will come out here, leading to BOCH3, 3 minus MgBr plus. Now, again, we'll use H3O plus H2O to get back into a neutral state for boron. And with that, we can now have BOH2 with OCH3. This is still in the same position. Oops, technology. This part will still be in the same position. We'll have then 3CH3OH plus Mg2 plus Br minus. Now lastly, I think the most important, and my favorite, is the het coupling. And this coupling is pretty interesting because the insertion step must occur in a syn manner, and that's because the reaction is intramolecular. So when we're thinking about this, we have, for example, this hydrogen plus here, and then right here is what we call the olefin, and this will be used when combining and rotating our reaction. So when we'll use PD, OAC, and O toluol 3, sorry, bad handwriting, and ET 3N. Essentially, because we see here as an E configuration, it will internally rotate, creating this. Let's leave it here. SO. The olefin now bonds, instead of the bromine, it will bond as a carbon to our primary reaction here. So that's how we do it, and hope you enjoy the video.